Alright everyone, let's talk about Chapter 8 here and get started right away. Chapter 8 is about Earth as a planet, so we're going to try to contextualize Earth and compare it to other planets and see what's going on. So we'll talk about the global perspective, just Earth as a thing. We'll talk about its crust, its atmosphere, life a little bit, climate change, and how space influences life on Earth. So planets lacking atmospheres are covered in craters, like the Moon, Mercury, but Earth doesn't have much craters, okay, so that's something to notice. We have received the same amount of things hitting us, okay, but we don't have evidence of it. So we have an atmosphere, we have oceans, we have tectonic plates, volcanoes and everything. So what can this tell us about the history of the planet? So that's what you should be thinking of as we get started. Our first step in exploring the solar system begins with studying the Earth, okay? NASA does planetary science. Why? Because Earth is a planet. So by studying Earth, we can learn about other planets and vice versa. So in this chapter, we examine the composition and structure of our planet with its ocean and atmosphere. We also ask how it came to be and how it compares to other planets. So we want to describe the components of Earth's interior, explain how scientists determined its structure. We want to specify the origin, size, and extent of Earth's magnetic field. And that's it. So Earth is a medium-sized planet. It is primarily composed of heavy elements like iron, silicon, and oxygen. This is very different than the hydrogen and helium that are found in stars like the Sun and others. It's important to notice that it's the only planet in our solar system that is just right for liquid water on its surface and the development of life. So we say that Earth is in what's called the Goldilocks zone, or the habitable zone of the Sun, because it's not too hot, not too cold. So it's difficult to study the interior of the planet Earth, but we are an industrious people, and we have figured out some tricks. We actually use earthquakes to visualize Earth's interior. In the same way that an ultrasound can study a baby or some other issue inside your body, we reflect sound waves, and as they bounce off the different layers of the Earth, we can measure how long that takes and get an idea of how far away the different layers are. And depending on the amplitudes of the bounces, we can determine what it's actually made out of. This is what we've got. Okay, a very cartoonish picture of the inside of the planet Earth. So the crust that we live on is very thin, and it's very not very thick. It's on the surface. Then you have the mantle, the outer core, and the inner core, and that's the general composition of the Earth as far as we can tell. There are two types of Earth's crust on this crust thing: the crust that's under the ocean, which is about 55% of the Earth, and the crust we're walking on, the continental crust. Some of that is under parts of the ocean, but there's two main types. The crust is the easiest to study, but it only makes up about 0.3% of the mass of the Earth, so it's not that much, but it's easy to study. The largest part of the inner Earth is called the mantle. It is more or less solid, but it's hot and dense enough to make rocks a little mushy. So just to give you an idea, the center of the Earth is the densest, heaviest stuff. The separation of Earth into the different layers is just like olive oil Italian dressing sitting on the counter. It separates into layers, and that layer separation, the heaviest stuff sinks to the center of the Earth and the lightest stuff floats on the surface. That's called differentiation. That's an important concept. Okay, Earth's core is larger than the planet Mercury. The outer core is liquid. The inner core is probably solid, just to give you an idea. And again, this separation is called differentiation. That's a key word. Make sure you pay attention to that. Okay, the core is rotating around Earth, and that generates a magnetic field. The region outside the Earth where the magnetic field exists is called the magnetosphere. This is the magnetosphere. It's because the Earth's core is rotating, and it creates this magnetic field around the Earth. The magnetosphere was first observed by Explorer 1, which was the United States' first satellite, and it was built by James Van Allen at the University of Iowa, so there's a little bit of a famous thing there. Okay, so now we're going to talk about Earth's crust and denote the primary types of rock that constitutes Earth's crust, explain the theory of plate tectonics, describe the difference between rift and subduction zones, describe the relationship between fault zones and mountain building, and then explain the various types of volcanic activity occurring on the Earth. Earth's crust is primarily made of oceanic basalt and continental granite. So the oceanic layers are made of basalt, and the continental crust parts are made out of mainly a granite type material. Both are called igneous rock, which is rock that has cooled from a molten state. So in other words, lava. There are two other uncommon types of rock, sedimentary and metamorphic. These aren't common on the Earth. Metamorphic is rock that is transformed in chemical or other ways from one rock to another. Not super common. Sedimentary is like sandstone, things like that. There's also a category of rock which is not on Earth anymore, and it's called primitive rock, and it's rock that has not undergone any transformations or changes since it formed in the original solar system when the planet Earth formed and the sun formed. We have to find that in asteroids and comets, so that's why we send missions there, is to study the very infantile rock, I guess. So Earth's crust is broke into plates. The theory of motion of these plates is called plate tectonics. So these are the different plates that we have, and you can see that Africa and South America, they fit nicely together because they were once in contact, and they've been even today they're still slowly moving apart from each other. This you see these arrows, these spreading centers are spreading the layers apart. Okay, so new crust is added to Earth's surface at rift zones. Okay, and then old crust has to go somewhere when new crust is added, so that is forced under other plates at subduction zones. And volcanoes and earthquakes take place at these subduction zones, and most of these big tsunamis and earthquakes in Japan take place along these the Ring of Fire. Okay, so here's a picture of a rift zone. So you got a rift zone where the lava is coming out and magma is pushing up, and then the crust is being formed and pushing out. So it's basically like pulling apart the surface of the Earth, and then all new molten stuff oozes up and comes out and creates more stuff. And then over here you've got a subduction area where this plate is pushing into that plate and getting forced down below it, and eventually it's gonna and then boing, and that's gonna be a big earthquake. Okay, so as crustal plates slide against each other this way, they create faults. So if we go back to this picture, you can see that, like the San Andreas fault here in California, the plates are not spreading or combining, they're rubbing against each other this way, and the same thing, they kind of and that's what causes those big earthquakes. So the rubbing creates earthquakes. Yeah, that's it. All right, so Earth's atmosphere then, and that's a picture of the San Andreas fault there in California. So Earth's atmosphere is, we want to differentiate the different layers of Earth's atmosphere. We want to describe the chemical composition and possible origins of our atmosphere, and explain the difference between weather and climate. Okay, so most of the atmosphere is concentrated at the surface of the Earth. This region is called the troposphere. That's where we are. Convection causes hot air to rise and cold air to fall, and it circulates like this, and that generates clouds and wind. The temperature drops dramatically as you go up in the atmosphere until you reach the stratosphere, and in the stratosphere there are no clouds anymore. You are above them. And then above that is the ozone layer, and the ozone layer is a layer of oxygen 3, or heavy oxygen, which is really good at absorbing ultraviolet light. And in the 1980s, scientists realized that there was a giant ozone hole developing above Antarctica, and the depletion of ozone in our atmosphere was causing that. Where was ozone? Why was ozone disappearing? It was because of CFCs. Where is that? Yeah, chlorofluorocarbons. I knew that word. What the heck? Yes, chlorofluorocarbons, CFCs, leaking from industrial processes or being used in that. When it gets into the atmosphere, it combines with O3, breaks it apart. Okay, so in the 1980s, the Montreal Accord, or the Montreal Protocol, banned CFCs. All the nations agreed to it, and the ozone hole has been closing up ever since, and ozone has stopped being depleted. Okay, so this is the temperature as a function of height, and it shows you that it gets colder until the stratosphere, and then it kind of levels off here, gets hotter a little bit in the ozone layer, cools back off, and then gets really hot at the ionosphere at the very top of the atmosphere. At Earth's surface, the atmosphere is 78% nitrogen and 21% oxygen, 1% argon. Did you know that you are breathing some argon right now? All planets with atmospheres have weather, which is the name we give to the circulation of the atmosphere. Weather changes day to day, minute to minute. Climate is the term that refers to the long-term averages of fundamental quantities, like the average temperature in the summer, or the average temperature in the winter, something like that, or the average number of hurricanes per season. So the best example of major climate change is when Earth goes through periods called ice ages. The last ice age ended about 14,000 years ago and lasted about 20,000 years. This is a picture showing how far the glaciers went down. So you can see they covered the state of Iowa, they went down in Missouri, that part of the region, down to New York, Boston, was under layers, 2-kilometer thickness of ice. And that's because we start to drift away from the sun in the winter, and sometimes our orbit gives us less sunlight. So that's the difference between weather and climate. Life, chemical evolution, and climate change. We want to understand the origins and diversity of life on Earth, explain the ways that life and geological activity have influenced the evolution of the atmosphere, and describe the causes and effects of the greenhouse effect and then global warming, and then describe the impact of human activity on our planet's atmosphere and ecology. So as far as we know, Earth appears to be the only world with life on it. The origin and development of life is an important part of Earth's story, and life arose early and has been interacting with Earth's environment for billions of years, adapting through evolution. The study of the coevolution of our planet and life together is a part of the field called astrobiology, which tries to understand the relationship between life and the rest of stuff. Life has existed on Earth in some form for the last 4 billion years almost, and about 3.5 billion years ago, life was sophisticated enough to produce what are called stromatolites, and they're these rock formations, which are really intricate, and there's a cross-section of the stromatolites showing the layers. Basically, they poop out a layer and climb on top of the poop, and they keep climbing and making these layers. All right, when life started, Earth's atmosphere was very different. It was entirely carbon dioxide and methane, but it didn't have any oxygen in the form of gas. So in addition to studying fossils, we can also study the history of life using genomics, which is the study of genetic information shared by life. This you can construct a tree of life, which shows the network of relationships between evolutionary as things branched off or their shared ancestries through common generations. So this is an example of the tree of life. You got some animals out here, but if we go far enough back, we all find our common ancestor in the single-celled organism. Okay, then it touches on briefly panspermia, which is, it's possible that Mars, since Mars cooled off before Earth did, life might have started on Mars and then landed on Earth, and Earth was, more successful as a planet. It's not frozen and dead now. So it's possible that life began somewhere else in the solar system or the universe and made its way to Earth and seeded it. So the evolution of the atmosphere, I mentioned that when life first formed, it was primarily carbon dioxide. Cyanobacteria, or blue-green algae, eats carbon dioxide and spits out oxygen. So most of our atmosphere, the reason our atmosphere is rich in oxygen is because of cyanobacteria and other life. The development of life changed our atmosphere from carbon dioxide to oxygen. We use oxygen, we breathe it in to help take the energy out of the food we eat. That's one of the main things. So we evolved to breathe basically the waste product of plants. So plants are exhausting oxygen, and then we developed to breathe that waste. So the planet Mercury reaches 400 degrees Celsius during the day, but at night it gets as cold as minus 200 C because it has no atmosphere to regulate its temperature. But Venus is even hotter than Mercury all the time, and it's twice as far away from the sun as Mercury is. So what's going on there? This is due to Venus's thick atmosphere. Venus's atmosphere is composed of greenhouse gases. These are gases which absorb and emit infrared radiation easily. Venus has a runaway greenhouse effect. Okay, so it's just super hot there. Basically, light rays come in and they heat the surface of the Earth, which emits infrared radiation, which is heat energy. And the clouds, water vapor, carbon dioxide, methane, greenhouse gases absorb and they just reflect that infrared and they just bounce it around a little bit longer. It's a blanket. It's like wearing a blanket. You know that you go outside and you're freezing and you put on just a thin little jacket and suddenly you feel pretty good. So it doesn't take much to regulate your temperature, okay? The same thing, our atmosphere is as thin as a saran wrap on a basketball, and that's enough to keep us from freezing solid. Because without our greenhouse gases, Earth would be frozen solid. Or at least the oceans would be frozen. So since the Industrial Revolution, however, the percent of carbon dioxide in our atmosphere has been going up. This has led to Earth, we're just getting better, we're getting a thicker blanket, so it's getting warmer. This is a measurement of the carbon dioxide from a island in Hawaii, to avoid, being, this is an area in the middle of the ocean, so it shouldn't have locally high amounts of carbon dioxide from an industry. So this is the mixed atmosphere, the baseline carbon dioxide way out in the middle of nowhere, and you can see it's just been going up like crazy. So Earth has been here so long and it's so big that some people have trouble accepting that humans can have an impact on the planet, but where we live right now, in this time, we have created enough of an effect in the geologic record of the Earth so that we anthropologists call this the Anthropocene. The activity of the evidence of human activity is so striking that it's hard to ignore. So if an alien species came in a million years, they would see evidence of this time period in the geologic record globally. There would be an obvious effect on the entire planet, which would not be able to be erased. Okay, so cosmic influences. This is basically about impacts, asteroids. So learning objectives. We want to explain the scarcity of impact craters on Earth compared with other planets and moons. And we want to describe the evidence for recent impacts on Earth, as well as detail how a massive impact changed the conditions for life on Earth, leading to the extinction of the dinosaurs. And we also want to describe how impacts have influenced the evolution of life on Earth, and then discuss the search for objects that could potentially collide with our planet. So there's lots of craters on Earth, actually, but most of them are severely eroded and difficult to see. We have rain and wind and volcanoes and earthquakes and all sorts of stuff to erase the activity or hide it. And most of our planet's covered in water, so if an asteroid hits water, it doesn't leave a mark. This is an example of a crater in Algeria. There's an example in Siberia, the Tunguska event. In 1908, an asteroid entered the atmosphere, blew up in the atmosphere before it hit the ground, but it was a 5 megaton blast, equivalent to a 5 megaton nuclear explosion. So pretty severe, and it felled all these trees over a very large area. This picture was taken 21 years after the event, apparently. This is about 50,000 years ago, the Barringer crater, or what's called Meteor Crater in Arizona. You can visit that. It's just outside Phoenix. It's pretty big. It's probably the most well-preserved crater on planet Earth right now. So those craters aren't such a big deal. You wouldn't want to be anywhere right near it, but if you're in Phoenix, you probably wouldn't notice an issue. But there have been 5 major mass extinctions in Earth's history. There's been a dozen or so that are, you could measure, but 5 major ones, like completely, nearly wiping out all of life. And climate changes, ice ages, things like that cause mass extinctions. But the one that we think about all the time is the one that killed the dinosaurs, because who doesn't love dinosaurs? 65 million years ago, an asteroid killed almost all life on Earth, including the dinosaurs. It hit Mexico on the Yucatan Peninsula, out here, the Chicxulub crater, and it's likely that Earth will get hit by asteroids in the future, It's important that we prepare for such an occasion because it's important, but it's also nearly impossible to do so. Why? Because asteroids are small, and you don't really tell that they are headed towards you until they are pretty much, you can't stop them. So, like the asteroid that killed the dinosaurs, I think we'd just have a few minutes of notice before we would see it coming our way. So, chew on that, because somebody's going to have to deal with that someday. Hopefully it's not us. But anyway, so this impact crater, you look at it and you say, well, that's pretty small compared to the, look at this thing. That's pretty small compared to the Earth, but what it did was pretty dramatic. It created massive tsunamis, like hundreds of kilometers tall, that wiped out a lot of the stuff on the land. It ejected a lot of stuff out into space, and as it fell back down to the Earth, it created shooting stars. But the thing about shooting stars is they could be pea-sized, and a pea could release enough energy to really light up and heat the atmosphere. So you imagine huge chunks of stuff, huge numbers of it, falling back to Earth and heating up. It actually heat up the atmosphere so that the surface of the Earth was the temperature of a pizza oven, like 400 degrees. And so everything just caught on fire. And so a lot of bad things happened all at once, and everything died. Okay, so that's everything. See you guys later.